am Tanusri. I will be presenting the introduction. First is problem statement. Water quality is a critical issue affecting ecosystems, human health, and economic activities. With increasing industrialization, urbanization, and agricultural activities, the contamination of water bodies has become a significant concern. Pollutants such as heavy metals, chemicals, and biological contaminants have adverse effects on aquatic life and human health. Therefore, monitoring water quality is essential for managing water resources, ensuring safe drinking water, and maintaining ecological balance. Next is our objective. We have 3 objectives. First, to analyze the water quality dataset using various machine learning models. Second, to compare the performance of different models in predicting key water quality parameters such as dissolved oxygen, pH, and turbidity. The last objective is to develop a reliable model that can be used for real-time monitoring and decision support in water quality management.
Good evening, I'm Shafira and I will be presenting the business process and the methodology that is being used in this study. For the business process, the first phase is collecting, gathering raw data from various sources. The data might consist of various water quality parameters such as pH, temperature, salinity, dissolved oxygen, and turbidity. Ensuring the data is collected accurately and timely is crucial for reliable analysis. The second phase is preparing, cleaning, organizing, and transforming data for analysis. Once the raw data is collected, it often contains inconsistencies, missing values, and potential errors that need to be addressed. Data preparation involves data cleaning, data transformation, and data organization. The third phase is analyzing, exploring, modeling, and visualizing data to uncover insights. This step involves a deep dive into the prepared data to extract meaningful insights. The last phase is communicating, sharing findings with others through effective visualizations. The final steps involve disseminating the insights gained from the analysis to stakeholders such as policymakers, water management authorities, and the public. The next is the methodology. The methodology that we use in this study is cross-industry standard process for data mining. The first phase is business understanding. Define the objective and scope of the project, which is to predict water quality based on various parameters to identify and classify the levels of dissolved oxygen. The second phase is data understanding. Load, inspect, and understand the data by checking the columns' names, structure, and summary of the dataset before handling missing values. The third phase is data preparation. Handling missing values, outliers, and visualize the data by imputing missing values, normalize data, and split into training and testing sets. The fourth phase is modeling. Build and train various models such as knife-based, decision tree, random forest, and one-row models. The fifth phase is evaluation. Evaluate and compare the performance of models using the confusion matrices and accuracy scores to assess model performance. And the last phase is deployment. Prepare the model for deployment or report the findings by documenting the entire process and results and deploy the model if applicable.
Hi, my name is Nur Hasana Binti Mubarak, and right now I'm going to talk about the results and findings that we have obtained regarding this dataset. Through our analysis, we first handle those missing values by replacing them with median and mean values for key variables such as dissolved oxygens, pH temperatures, and also chlorophyll, just to ensure those data integrity. We also remove those invalid data entries, particularly negative values for dissolved oxygens, to maintain those accuracy. Various visualization techniques, including histograms, density plots, and scatter plots, were employed to explore distributions and relationships of the key variables. In model training and evaluations, the decision tree model achieved the highest accuracy at 82%, outperforming the naive Bayes and random forest models, which also perform well, but with slightly lower accuracy. However, the one-row model had the lowest accuracy, but improving it could involve feature selections based on correlations and better binding of continuous variables. And overall, the decision tree model demonstrated the best performance in predicting those dissolved oxygen levels, while our data pre-processing steps were crucial for the success of our modeling efforts.
I am Anis Zakira, so I will continue on to the advantages and disadvantages of each models we use in our project. Firstly, we have naive Bayes. One of the main advantages of the naive Bayes model is the simplicity of its calculation for conditional probabilities. The training process is very quick because probabilities are directly computed without the need for iterative processes. This is particularly useful in scenarios where speed is crucial. However, the naive Bayes model has its drawbacks. In real-world scenarios, features often depend on each other, making the model's independence assumption unrealistic. Additionally, if a word appears in the test data but not in the training data, it can result in a zero probability for the class, which is a significant limitation. In addition, for the decision tree model, the advantages of this model is that it requires minimal effort for data preparation during pre-processing. It does not require data normalization or scaling, and missing values do not significantly affect the model. This makes it a very flexible and convenient choice for many applications. Even so, small changes in the data can lead to large changes in the tree structure, causing instability. Additionally, the calculations can become more complex compared to other algorithms, and training the model can take more time. Furthermore, we have random forest models, where these models naturally deals with missing data and outliers without pre-processing steps such as imputation or removal. It can also manage a mix of numerical and categorical data, making it a versatile option. However, the random forest model can be slower in making prediction, as each observation must pass through multiple trees. Additionally, it can be difficult to understand the logic behind predictions due to the combination of many trees. And lastly, we have one-rule model. The one-rule model is simple and easy to understand. It is very fast to train and predict, making it suitable for quick and straightforward tasks. However, the one-rule model is less accurate and more simplistic, making it less suitable for complex data. Its simplicity can be a limitation in cases where more nuance and detailed analysis is required. Next, for the impacts of the study, which firstly about improved water quality monitoring. The developed models can predict water quality parameters with high accuracy. This leads to more effective monitoring and management of water resources. With accurate predictions, we can ensure that water resources are managed efficiently. This is crucial for maintaining the sustainability of our water supply and ensuring that the quality remains high. Next, these models also can aid in informed decision making. This study provides precise and timely data on water quality, aiding policymakers and water management authorities in making informed decisions. Having access to accurate and up-to-date data allows authorities to respond quickly to changes in water quality. This can lead to better policy decisions and more effective management strategies, ultimately benefiting communities that rely on these water resources. Lastly, the impact on environmental protection and public health. Monitoring and predicting water quality changes help identify pollution sources, detecting potential hazard early, and ensuring safe drinking water. Early detection of pollution sources allows for prompt action to mitigate the impact on the environment and public health. Ensuring safe drinking water is critical for preventing waterborne diseases and protecting overall community health. In conclusion, this study has a variety of machine learning models that were assessed to predict important water quality parameters. The data was pre-processed to manage missing values and outliers, and visualization were used to understand the relationships between the different parameters. The evaluated models included naive Bayes, decision tree, random forest, and one-row models. Among these models, the decision tree computed the highest accuracy in predicting dissolved oxygen levels. Additionally, naive Bayes and random forest also perform well, offering faster training times and ease of interpretation. Although 1R model, due to its simplicity, provides a good baseline, it was outperformed by the more complex models in terms of accuracy. This comprehensive evaluation has allowed us to understand the strengths and weaknesses of each model in the context of water quality prediction. We hope our findings contribute valuable insight for future research and practical applications in water resource management.